So welcome to Math341, lecture 21. What we're going to do today is we're going to start looking at the central limit theorem. All right? I hope the hat is obvious. It's because I'm actually flying today. No, okay. Right, where am I flying to? Who knows the airport codes? Wow.
Charlotte?
Charlotte, yes, CLT is Charlotte. All right. So central limit theorem. So the idea is, let's let x1 through xn be nice. Nice is just a placeholder for insert technical conditions here. And depending on how far you want to push things, it becomes a game, almost like a one-upsmanship. Oh yeah? Well, I can prove the result assuming only just this. Right? We will frequently assume far more than is the minimum. There is a whole slew of central limit type theorems. We'll do a simple case. We will assume finite mean, variance, higher moments, with a good growth rate. And then we will talk about what that means later. So we will let Zn be x1 plus xn minus n times mu divided by sigma square root of n. And if you do the calculation, the expected value of Zn is 0, and the variance of Zn is 1. So what we're essentially doing is we're standardizing our random variables. And since we know what the mean is, we know how the sum x1 through xn is growing. It's going to look like n times mu, so we might as well subtract that off because we know it. And be nice, and I should say independent. And because they're independent, we know the variance of the sum is the sum of the variances. So the variance of x1 through xn is going to be n sigma squared. So its standard deviation is going to be the square root of that, or sigma square root of n. Subtracting off the n mu does not change the variance. So this quantity is going to have mean 0 and variance 1. And then the result is then Zn converges to being normally distributed with mean 0 and variance 1. So I am going to be very vague right now as to what do I mean by it converges. Right? Essentially what I mean is if I want to calculate probabilities of Zn, I can essentially calculate them by looking at probabilities of the standard normal. So what I want to do today is discuss the central limit theorem in a simple special case. I will go through the calculation in great detail. I had you all watch a video for Wednesday. What I want to do is potentially move 20 or 30 minutes of material each week, not a whole lecture, just a subset of the lecture, to online to free up a little bit more time to do problems and programming in class. Not an entire lecture. So I want you to just think again about how that worked and how if you would like to do more problems and programming. If nobody wants to, happy to do all the details. But there are parts of today's lecture where you could just easily skip some of these calculations and just leave them. All right, what is the simplest possible random variable you can give me? The simplest. Okay, so it only takes on one value. So whatever you give me, okay, let's say you're going to ask me for a sports team, and I'm going to randomly choose among all sports teams, and the probability I say Red Sox will be 100%. Right? This is not a really interesting random variable to study. Well, first of all, we wouldn't allow me to even have this as my random variable. Why? Why can't Red Sox be my random variable?
It's not random?
Nope. It's fine to be deterministic, but what must all random variables be?
Don't you have to be 0 at all other possibilities?
Sure, so related to that,
It has to be a number.
it has to be a number. Red Sox is not a number. Okay? So let's say whatever when you're going to ask me for a number, I'm always going to say 2004, 2004, 2004 with 100% certainty. Now that's a random variable. If I want to study sums of that random variable, it's not hard. If each random variable is 2004 with 100% certainty, then this sum is just going to be n times 2004. This is not worth studying. So we have to go to a slightly more general situation. So instead of always being one specific value, what's the next thing we could study? I'm sorry?
The uniform?
Uniform on what? On two values. And in fact, it doesn't have to be uniform on two values, but just we only take on two values. Which two values should we take on? One possibility is 0 and 1. That is a subset of the people. There is a large group of people who would say 0 and 1. There's also another population, which I actually prefer. 1 and minus 1. So the advantage of the 1 minus 1 camp is the mean is now 0 if the random variable is uniform, if it's fair. So what you'll frequently do is you'll flip a fair coin. If you get a heads, it's +1. If you get a tails, it's -1. You don't have to do a fair coin. It doesn't have to be 50-50. If you do that, it just makes the calculation easier. And when you see all the algebra that happens now, you'll be very grateful for anything to make the algebra easier. I know as the person who has to write it, I'm grateful for anything to make the algebra easier. All right. The motivation for something like this is, are there anybody here taking physics? In particular, statistical mechanics? Have you done okay, so has anybody here done the lamppost problem?
Yeah.
Okay, excellent. So the way it was phrased in my stat mech book when I was in college is, imagine you have a drunk who is so drunk, so completely wasted. I know it's hard for you to imagine anybody like that. And she's like, oh yeah, my friend. That they have a 50-50 chance of staggering either one way or the other. And they keep staggering, and a certain amount of time goes on, and you want to know, where will your friend be? And the simple case is you assume your friend only lives on a one-dimensional surface. Okay? And then you could ask questions such as, what's the probability after n steps my friend is at least this far away? What's the probability my friend actually staggers back home? And it turns out, with 100% certainty, you will actually stagger back home at some point. Then you could ask what happens in 2 dimensions. And the problem really gets interesting once you get into 3 dimensions. I remember one of my math professors said, this is why we live in a 3-dimensional space, because it's the lowest integral dimensional space where the world is interesting for drunks. You could make the problem a little bit more interesting. What could you do to help your friend who's drunk? What might you give them?
More alcohol.
That might be more interesting for you. If you wanted to help your friend, what might you do? This is probably a hard question for you because none of you, of course, have ever seen anybody drunk. You might give them coffee. So you could imagine, and if anybody wants to work on this as a problem, imagine you have the real line now where at different places you either have like Starbucks or coffee shops, or you have bars, say most taverns and stuff like that. And when the person staggers, if they get to a coffee shop, they get some coffee, and they become a little bit less drunk, and they now have a slightly higher probability of staggering home. And if they get to a bar, they get a little bit more drunk. And you could ask, what happens in the dynamics now where you have a process where your probabilities are not static? So if anybody's interested in a problem like this would be a great thing to try to simulate. We will do the simple case. So it's example. So xi is equal to 1 with probability 1/2 and -1 with probability 1/2. This is not quite a binomial, this is not quite a Bernoulli random variable. A Bernoulli random variable should be 0 and 1. So if you wanted a Bernoulli, what you could do is you could let yi equal xi plus 1 divided by 2. And if I looked at this, then the yi's would be Bernoulli random variables, just taking on the values 0 and 1, and then we would be back in the situation you wanted. It is fine to study either one of these. They're essentially equivalent. Okay? One advantage of looking at the Bernoullis is if we then try to calculate what's the sum of the xi's, well, what distribution would be the sum? What would be the sum of the yi's? What would be that distribution? Binomial. So then we would get a binomial. And then you would have, y1 plus yn is binomial and 1/2 because things are fair. So we could write it like this. We're not going to. We will just analyze things directly. And then what I'm going to do is I'm going to look at some number of tosses. So I will assume 2n tosses. What can you tell me about my location from the origin after 2n tosses? What fact do you immediately know?
Between -2n and 2n.
So you know we're between 9 and 10. Given that you can only move 1 or -1, you can't move further than that. Okay, good. What else do we know? Use a little basic number theory. Yes?
It must be an even number.
Yes. Also even. So we know the probability that you are 1 or 3 or -17 units from the origin is 0. So this discreteness is actually going to cause a little bit of a problem. We're going to essentially have double the Gaussian probability at even integers and 0 at the others. But on average, if you look at pairs, it's going to be fine. So what we would really want to do is, if this is, say, 84, here's 85, here's 86, 83, 82. What I would do is I would take this as my box. I would take 84 plus or minus 1. And then I would take, for 82, I would take 82 plus or minus 1. And whatever probability I get, I would smear that probability over that whole box. And that's how it would essentially go from this discrete thing to a continuous thing. Okay, any questions with this? We actually saw something similar to this when we were looking at the Pythagorean stuff, when we said we want the bins to be centered at half integers, just so that the scores are in a nice place. Okay. I'm sorry, we want the scores centered at the integers with length half an integer in each direction so that the scores are all well separated. All right, so we know that they're between us. So let's calculate what is the probability that, let's say, yn is going to be x1 or y2n, I guess, plus x2n. So what's the probability that y2n equals 2k? I know it has to be an even number, so let me write it as 2k. So how would you end up 2k steps from the origin? What must be true? You need to tell me how many heads, how many tails, and what do we know their total must be? 2n. So when you want to write this, it seems reasonable to start writing it as n and n. And then what's the excess in number of heads to number of tails?
Subtract.
Okay. So how many heads do you think I have and how many tails do you think I have? I've got a net 2k. So heads minus tails has to be 2k, and they have to add up to, so they have to add up, it seems very reasonable to write it as n plus and n minus. And well, if I've got to have a difference of 2k, it's really telling me I got to look at this, n plus k and n minus k. So now I have 2n tosses. I need exactly n plus k of them to be heads. Have you seen binomial coefficients? Excellent. So that's going to give me n plus k heads. And then the next factor is I have n minus k left that all have to be tails. Is there any need to write n minus k, choose it? No, this is just 1. So we don't need to clutter things up with this. Now we have the probability of a head, and we have n plus k heads, and we have the probability of a tail, and we have n minus k tails. And now you can see one of the first reasons why we want to assume the coin is fair. If the coin was not fair, this would be p and 1 minus p. And then you would see, oh, there's a k dependence. We're both going to have an n, but we're going to have a p to the k and a 1 minus p to the negative k. But because it's the same, what is this factor simplified to? A half to the 2n. So we just get to divide by 2 to the 2n. So this is the advantage of looking at the fair coin. And this is where we use it tremendously. So now we want to analyze this expression. And we want to see, what does this look like? What tool might be useful to analyze this binomial coefficient? I see a couple people smiling. What should we use?
So in your Stirling formula video you mentioned you might want to use that.
Yeah. There's a reason why this lecture is following the lecture on Stirling's formula. Stirling's formula is building up some tools. So Stirling tells us that m factorial is approximately m to the m e to the minus m square root of 2 pi m. And if you want to go further, the next term is of size, I think it's either plus or minus 1 over 12m. I forget what the next one is. If m is huge, think of m as like Avogadro's number, 10 to the 23rd. This is still a very large number when you multiply the main term by 1 over m. But it is small relative to the main term. And so in our analysis, we can drop the lower order terms in Stirling, and we will just focus on the main part. And so we can use this to analyze, 2n choose n plus k is going to be 2n factorial over n plus k factorial and n minus k factorial. So in order to use Stirling's formula, what do I need to be true to use Stirling? So if I want to use Stirling's formula, what must be true about m? When is Stirling's formula good? When is it very accurate?
M large.
Yeah, when m is large. If m is small, this is very bad. So for this, I need all three factors to be large. 2 to the n is going to be large. Is it possible for n plus k or n minus k to be small? Yeah. If k is very close to n or very close to 0, then these numbers over here, it's not good to use Stirling. So I want to be able to justify using Stirling. So I need to show that k can't be too large. So k is the excess in the number of heads over the number of tails. Oh, I'm sorry, the way it's written, I'm sorry. I just need to keep k away from n or negative n. So need k far from plus or minus n. Well, we're flipping a fair coin 2n times. And k is the excess of heads over tails. Number of heads minus number of tails. What's the expected value of k? 0. And what's the variance, roughly in terms of n? How does the variance depend on n? No, I said the variance, but if I said the standard deviation, you'd be right. The variance looks like n, the standard deviation looks like square root of n. So because k is looking like square root of n, it's very unlikely k is going to be large enough to cause trouble. So what we need to do is we need to show what's the probability that k can't be too many standard deviations away from its mean of 0. This should hopefully tell you what result we want to use. Right? I want to bound the probability that k is many standard deviations away from its mean. What result do I use? I use Chebyshev, right? The whole point of Chebyshev is to investigate things on the natural scale. Chebyshev talks about what's the probability you are so many standard deviations away from the mean. Chebyshev, the actual value typically sucks. It is far from the truth. But that's fine. We don't need that much. We just need to show that k can't be that far away from n. Doesn't matter exactly how much we choose. A little bit. All right, so let's do some work. So the expected value of y2n is the sum of the expected values of the xi. This is by linearity. And since each of the xi's is 1/2 the time and negative 1/2 the time, this is just going to be 0. So this means the variance of y2n is just the expected value of y2n squared, because the expected value of yn is just 0. So we just need to calculate the second moment. Because the xi's are independent, we know the variance of y2n is the sum of the variances of the xi's. And because each of the xi's has expected value 0, each of these is just the sum of the expected value of xi squared minus xi squared, and these are all 0. So we just need to calculate the sum of the expected value of xi squared. So this will be a sum. I goes from 1 to 2n. And now what's the expected value of xi squared? We get a value of 1 squared with probability of 1/2. And we get a value of negative 1 squared with probability of 1/2. All right, 1 squared times 1/2 plus negative 1 squared times 1/2 is just 1. So we have a sum of 1, 2n times, it's just 2n. So we get the standard deviation of y2n is just the square root of 2n. And this fixes our intuition, this supports our intuition that it really is fluctuations on the order of square root of n. I don't really care about the constant square root of 2. I need it if I want to do the calculation correctly, but I really care about just the growth rate with n. The fluctuations are growing like square root of n. What this means is the probability that k is even as large as n to the quarter is insignificant. So I'm going to just record up here that this is the variance is 2n. All right. Can I erase the lines over here? Does everybody have this stuff? Yes?
Quick question. Why
Yes.
do you say expected value of y and square is equal to 0? Second line to the right.
Oh, it should be y2n.
And why is that equal to 0?
Well, because the expected value of the y2n's is the sum of the expected value of the xi's. And the xi's all have mean 0. So this is the reason why I like to use not the Bernoulli random variables, but these shifted Bernoulli random variables, because now all of my expectations are 0. Now, if I have expectations of squares, different story. All right. So let's keep going with the calculation. So now we'll use Chebyshev. And again, this is far from the truth, but we don't need to be close to the truth. The probability that y2n minus its mean is greater than or equal to, I can't use k for the number of standard deviations. Why can't I use k for the number of standard deviations? Yeah, k is already in play. Do not use the same letter again and again and again. I once took a math class where the letter F on the left-hand side meant something different than the letter F on the right-hand side. And it was a real eureka moment when we realized, oh, it's not the same. Oh, wonderful. Okay. I'm refereeing a paper right now where the person has redefined the real numbers. Not a good idea. So I need some letter. I'll use the letter A. I want to be at least A standard deviations, 2 square roots of n. This is going to be less equal to 1 over A squared. So for example, if I take A to be, I don't know, n to the 1/4, this means the probability that y2n is greater than or equal to the square root of 2 n to the 3/4 is less equal to 1 over the square root of n, because I get to square this. That's essentially 0. Think of n like Avogadro's number, 10 to the 23rd. You don't even need to take a as large as n to the 1/4. You could even do a equals log n. Or you could do a equals log n. When you put that down here, it's going to give you a probability that goes to 0. So what this essentially tells us is, without loss of generality, a can be anything going to infinity, and that's going to force our k's to be essentially within a small amount of 0. Once you go up as high as log n or even log n, that's enough to have almost no probability in the limit. So the chance of making a mistake by using Stirling's formula here is negligible. So without loss of generality, we can assume k is very close to 0. That the probability that k is larger than that is insignificant, so I can focus my attention on small values of k. All right, any questions on this? Yes?
Is that a result of the probabilities being 1/2? This wouldn't apply. We had different probabilities for the point.
It would shift things a little bit. So if we didn't have probabilities 1/2, first of all, the mean wouldn't be 0. So it would shift k from having a mean of 0. But we would still be able to bound that these probabilities are going to be such that we have basically no chance that these are going to be small. Again, k has to be extremely close to n or negative n for us to run into trouble. If k is as large as n to the 0.9, that's insignificant in the limit. N is much, much larger than n to the 0.9 in the limit, even though n to the 0.9 can be huge. So, excellent questions to ask, but this allows us to focus on k in a very nice region. Okay. Any other questions so far? All right, can I erase all this? So I'm trying to keep both the statement and the setup on the board as long as possible. Pretty soon I'm going to give up. All right, there's a lot of algebra coming, but I want to try to see how long we can keep it. All right, so now we need to start doing the analysis. Okay, so if I look at the 2n factorial, that's pretty easy to analyze. So 2n factorial is going to be 2 to the 2n. So I'm just taking it's going to be 2n to the 2n, e to the minus 2n, square root of 2 pi times 2n. Oh, what do we get to divide our probability by? We get to divide it by 2 to the 2n. Look, I've got a 2 to the 2n, n to the 2n. The 2 to the 2n is going to cancel nicely. So 2n factorial divided by 2 to the 2n is just going to be n to the 2n, e to the minus 2n, square root of 2 pi times 2n. Okay? For the next piece, I'm going to look at n plus epsilon k factorial. What do you think the possible values of epsilon are? I'm trying to do a unified presentation. So what should my values of epsilon be? Well, the expressions I need to look at is n plus k and n minus k. So I'm going to just take epsilon to be either 1 or negative 1. If I write it like this, I can save some time on the blackboard. And I can handle both cases as much as possible the same way. And this way I don't have to do the analysis and say, and now we argue identically as we did before, except we have a negative sign. Let's just introduce an extra auxiliary quantity, epsilon, to help us. So this is going to be n plus epsilon k to the n plus epsilon k e to the negative n plus epsilon k square root of 2 pi n plus epsilon k. Now, in what's going on inside the square root, we know k is not that much larger than, square root of n. The probability k is larger than square root of n is essentially 0. We said once a is as large as log n, the probability is essentially 0. So k is really not going to get much larger than square root of n. So n plus epsilon k is essentially n. I can drop the epsilon k. So is everybody happy with dropping the epsilon k over here? Right? So now when we combine things, we'll have 2n choose n plus k divided by 2 to the 2n. And this will be approximately equal to the following. So I'll have this mess divided by this with epsilon, 1 and negative 1. So I'm going to have a n to the 2n, e to the minus 2n, a square root of 2 pi 2n, and then down below, I'll do one thing first. What might I want to pull out of this factor here? I'm going to pull out an n. If I pull out an n, I'll have an n to the n plus epsilon k, 1 plus epsilon k over n, e to the minus n plus epsilon k, square root of 2 pi n. And the reason is, when I do this now, I do this once with epsilon equals 1, and once with epsilon equals minus 1. So I have n to the n plus k, n to the n minus k. The plus and minus k cancel, and I get an n to the 2n. So I'm going to just try to do the algebra a little bit fast. Then I get, this has an n plus epsilon k up here. Then I'll have a 1 plus k over n to the n plus k. I'll have a 1 minus k over n to the n minus k. So now over here I get e to the negative n plus k. I get e to the negative n minus k. The k's again cancel, and I get e to the negative 2n. And I get a square root of 2 pi n twice. 2 pi n. All right. The e to the minus 2n's cancel. The n to the 2n's cancel. A 2 pi n cancels with a 2 pi n over here. And I'm left with a square root of 2. But I get to divide by square root of 2 here, so the square root of 2 cancels. I've got a 1 over square root of pi n. And then I have 1 over 1 plus k over n to the n plus k, and 1 minus k over n to the n minus k. And the question is, what does this product go to? Well, n is much larger than k. What does 1 plus k over n to the n go to? It goes to e to the k. And what does the other one go to? E to the minus k. So we are using one of the definitions of the exponential. Right? So the limit as big N goes to infinity of 1 plus u over n to the n is equal to e to the u. So we want to say 1 plus k over n to the n plus k, 1 minus k over n to the n minus k goes to, this factor goes to e to the k. This factor goes to e to the minus k. What does e to the k times e to the minus k go to? 1. All right, I should not be getting a probability of 1 uniformly. Where did we go wrong? So this is one of the really subtle things. You've got to be careful about interchanging limits. This is going to e to the k, if you just look at just this part, which is going to maybe infinity. This could be going to e to the minus k, which is going to potentially 0. So one term could be going off to infinity, one term could be going to minus infinity, could be going to 0. You can't take the limit of infinity times 0 by saying the limit of the product is the product of the limits. You've got to be more careful. So there's a couple of ways to do this. This is not one of them. What you could do is you could break it up into two terms. You could say, well, look, let me take the n's, and I've got 1 plus k over n to the n, 1 minus k over n to the n, and then I've got 1 plus k over n to the k, and then 1 minus k over n to the negative k. I could try to do something like this. What's nice is over here, this is just 1 minus k squared over n squared to the n. And I could try to say, well, this is maybe probably really, really small. Although k could be as large as square root of n. Oh, so if this is square root of n over n squared, this could look like 1 over n, and I'm raising it to, so maybe this is, so what this is telling you is this is a bad way to do the analysis. This is just very liable to make an error. So what should I do? How should I handle this product? If you've had a class with me, you know by now what to do. Logs, excellent, right? You have a Pavlovian response. Whenever you see a product, you take logarithms. So let's let P be that product. Then the log of P is going to be n plus k, the log of 1 plus k over n, plus n minus k, the log of 1 minus k over n. And now we'll use the log of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus dot dot, and the log of 1 minus x is negative x minus x squared over 2 minus x cubed over 3. These are the expansions. And when I look at this now, I get n plus k, and now let me start to expand this. So the first term I get is I get a k over n. Then I subtract off 1/2 k squared over n squared. The next, in the higher terms, I'll have a k over n cubed, a k over n to the 4th. Well, but k is really not much more than square root of n. So once you have a k cubed over n cubed, this is going to be at most a little bit more than n to the 3/2 upstairs. This is going to be like 1 over n to the 1.4. Right? We have at most a little bit more than n to the 1.5 over n to the 3. It's a little bit less than 1.5. I'm multiplying by n. Even when I multiply by a large number like n, this is going to be insignificant. Over here, since k could be roughly as large as n as square root of n, k squared could be of size n times n over n squared, that can contribute. But I don't need to look at the higher terms. So I can just make, it's approximately equal. And then the next one would be plus n minus k, and I would have negative k over n minus 1/2 k squared over n squared. And now it's the nightmare of just multiplying everything out. So the n times k over n, the n times negative k over n, those cancel. The k times k over n and the negative k times the k over n, they reinforce. All right, and so we'll have a k squared over n times 2. And that handles each of these terms touching the first one. Now for the next one, I'll have a n times negative 1/2 k squared n squared. And I'll have an n times negative 1/2 k squared over n squared. So they reinforce. So I'm going to get a minus k squared over n. And then the next one, I'm going to have a k cubed over n squared. K cubed is at most a little bit more than n to the 1.5. I don't need to worry about that. So it's approximately this, which is k squared over n, if I've done things correctly. This was in the denominator. So now, when I put the pieces together, we now have that the log of p is about this. So that means p is approximately e to the k squared over n. And that was in our denominator. So we got the probability that y2n equals 2k is approximately 1 over square root of pi n. And then we get This is now downstairs, so it comes upstairs, e to the negative k squared over n. And boy, is this looking a lot like a Gaussian. What's the variance supposed to be? It was erased. What's the variance supposed to be? I think it was 2n, right? Oh, and this should be, I shouldn't be using n's. My n should be, sorry, my n should be little n's. The variance is 2n, right? I want to view this as e to the negative k minus mu squared over 2 sigma squared. So I want to figure out how to write things. So I'm going to start playing some games. All right? So we can write this as approximately 1 over square root of 2 pi 2n, and then I'll put a 2 over here. Because you want to have 1 over square root of 2 pi sigma squared. So square root of 2, square root of 2, that doubles up the 2 over there. All right. Do I want to have a k squared? What do I want to have? It's not k. What do I want to have? I want to have 2k. So I want to write this as negative 2k minus 0 squared. So I've put up an extra factor of 4. So I have to put a factor of 4 down below. How should I write 4? No. 2 times 2. So I can write it as 2 times 2n. And now you can see there's the Gaussian. Here is the variance. Here's the mean. The only thing that makes it not quite a perfect Gaussian is we have this factor of 2. But I told you that's because of discreteness. Because we have to double things. And so we get a nice QED box, no algebraic mistakes worth mentioning. Okay? This is the proof in the special case. The general case is actually in some sense a little bit easier because you don't have to go through all of this algebra. But it's nice to see a proof of the central limit theorem in the simple case and see what do we need to make the analysis work. And a big part of it is at the end of the day it's pattern recognition. Can you recognize at the end that you have a Gaussian? Well, this leads naturally into the last bit of the lecture today, looking at Poisson random variables. So we have beautifully succeeded in looking at sums of coin flips. So let's say x lambda is Poisson with parameter lambda. This means the probability x equals n is lambda to the n, e to the minus lambda over n factorial. N is in 0, 1, 2. We've talked before about why we might care about this. So I'll do the special case. Let's say we have x5 plus x7. I'm just going to use specific numbers. And I'm going to, in a fit of inspiration, call this y12. All right? And we'll see what is the distribution of x5 plus x7. How do we find the distribution? What technique do we use to find the distribution of two independent random variables? How do we calculate the probability? What do we use? What's the name of the method? Convolution. So if we want to use the probability that y2n, well, that y12 equals m, this is going to be the sum, and goes from 0 to infinity, the probability that x5 equals, sorry, L goes from 0 to infinity, x5 equals L, and then the probability that x7 equals m minus L. Well, we know that since these are Poisson random variables, they only take on non-zero probabilities at non-negative integers. So we need L and m minus L to be greater than or equal to 0. So what does that allow us to restrict the range to? How high can L go? Someone over here say it? What's the highest L can get to? If I want both L and m minus L to be non-negative. Must be m. Because once L is greater than m, this would become negative. Okay, so L goes from 0 to m. All right, so now when we substitute in, we have a sum. L goes from 0 to m. The probability x5 equals L. Oh, well, that's fine. That's just going to be 5 to the L, e to the minus 5 over L factorial. And then the probability that x7 equals m minus L will be 7 to the m minus L, e to the negative 7 divided by m minus L factorial. It is screaming at you to pull out the e to the negative 5 and e to the negative 7. Right? So we get e to the negative 12. The sum, L goes from 0 to m. We have an L factorial and an m minus L factorial. What does that want? It's begging you for it. I'm sorry? What does it want upstairs? An m factorial. Well, you can't just multiply by m factorial. You have to divide by it. But let's divide by it outside the summation, because it doesn't depend on L. We've now just multiplied by 1. And now we have a 5 to the L, a 7 to the m minus L. Oh, this is the binomial theorem. This is just going to be 5 plus 7 to the m. So we get 5 plus 7 to the m, e to the negative 12 over m factorial. And of course, 5 plus 7 is also known as 12. So we get 12 to the m, e to the negative 12 over m factorial. Oh, what kind of random variable do you think this is? Poisson. And so we've basically just shown is a Poisson plus a Poisson is a new Poisson, and the parameter of the sum is the sum of the parameters. Is there anything special in this problem about 5 and 7? No. I'm a number theorist. 5 and 7 are special. They're a twin prime pair that has nothing to do with this. Any two numbers would work here. The sum of two Poissons is Poisson. So what would happen if you took Poisson with parameter 1 plus Poisson with parameter 1 plus Poisson with parameter 1 n times? You would get what? Poisson with parameter n. What should that be close to if n is large? Normal. You can actually prove Stirling's formula if you know the central limit theorem by applying it to sum of Poisson random variables. Because you know the sum of Poisson random variables is converging to the normal, you can actually use this to do Stirling's formula. Because we know what the probabilities have to be going to. So what's truly remarkable about this problem over here is we were able to figure out what the sum of these random variables are. So my question for you is, when can you do a method like this to determine what is going on in general? So this is moving into chapter 19 to generating functions. And the idea is going to be, can we find a way to work with sums of independent random variables and figure out what they're going to? Can we get a nice expression for what the distribution of the sum is? And the real concern we always have is uniqueness. Could you have two different processes go to the same value? And if you take complex analysis, you learn techniques to handle that. All right, this is a great place to stop. My hand is tired, too much algebra.